All right, so let's talk about 9C. So right now, so a few things that are on the agenda for you. We will have 9C today, 9D, Tuesday, Wednesday, 9E. So Tuesday or Wednesday next week, we will have a quiz on 9A through E. Okay? So just give you a heads up for that. So that would be a week from tomorrow or a week from Wednesday. We'll have a quiz. Okay, so the number E. The number E is just basically how did certain things come about. There are certain things that exist in math that we have this fascination with. You know, we have pi, we have E, we have all these other things. But basically, E was established by creating, so if you made this 2 over 2, you'd get 3 over 2 quantity squared. So that would give you 9 over 4. If you did this, that would give you 3 over 3. So it would get you 4 over 3 to the third power, which is 64 over 27. This one, that would be 4 over 4, so that becomes 5 over 4 raised to the fourth. So 5 times 5 times 5 times 5 is 625, I believe. And 4 times 4 is 16. 16 times 16 is 256. And so on and so forth. So this would have becomes 5 over 5, so that becomes 6 over 5. And then 6 to the fifth power is, I have no idea. There's Anna. So let's see. 6 raised to the fifth, clear. 6 raised to the fifth is a number that I definitely wouldn't have gotten in my head. And then 5 to the fifth. And it just keeps going and going. Okay, so this is just basically the sequence that they're dealing with is they're doing 1 plus 1 over n, and then you're raising to the second power. So as you improve this to become larger and larger and larger, it becomes the number E. Okay, and E itself does represent a number. It's e to the first as you have it sitting, and e to the first comes out to 2.72 roughly. So this is about 2.72. Okay, and I'm rounding it to 2 decimal places. It becomes an irrational number, goes on and on forever, and kind of similar to pi. So then Euler, it looks like Euler, but it's Euler, investigated this pattern even further, and they realized 10 to the first is 10, 10 to the second is 100, 1,000, 10,000, 100,000, million, 3, 4, 5, 6, so on and so forth. So basically, he was just deciphering what was happening with as I grew numbers and raised that. If I grew a number by a certain ratio to that, and again, this is E, which we said before on the last slide is 1 plus 1 over n raised to the n power, where n represents some sort of whole number. As we continue to get larger and larger and larger, you approach this. And I had called it 2.72 originally because I rounded it here, but of course this continues on forever and ever and ever. This is just a period that is not another decimal existing in the number. So this is the natural base E. Questions so far, my friends? Do we feel okay? Let me switch pages here. There we go. Okay, so now when we start dealing with these things like this, you're going to multiply those together, so you get negative 12, and that's e to the first times e to the second, so you're going to add the exponents. Is going to give me e to the third. And you can go ahead and stop there. There's going to be eventually a time where we're going to talk about how we'd plug that in. Power to power means I'd multiply the exponents, so I get e to the negative 8 which then would in turn become this 1 over e to the 8, so you're going to have a negative exponent. This particular one you put out at first. 6 over 2 is 3. And then tug of war with the e's, top wins by 4. You'd wind up with that. Okay, and this is simplifying and keeping it as base e. E follows all the same properties as a variable, though e is not a variable, because again, e is equal to 1 plus 1 over n raised to the n power. As n approaches infinity is how we get to e. Okay? Excuse me. All right, so 2 times the 1 out front is going to give me 2. Like bases, add the exponent, so x plus x is 2x. So I get 2e x plus 3, and that's my answer. The square root of 64 is 8. The square root of e to the 4 is e to the second. The square root of e to the x is e to the x. The reason that didn't break down is this would have broken down into 8 times 8 times e to the 4th times e to the x. This would have given me a perfect square, perfect square. This doesn't give me a perfect square, so it's left behind under the radical. Number 10, like bases, we're going to add the exponents. So I get 2x minus 2x, that's 0. So I wind up with e to the first, and that's done. And then if I had this, I have to recognize that I have e to the first on top. So I am technically doing a tug of war, but what I'm really doing is I'm going 1, subtract x plus 1, distribute the negative over the parentheses. So those cancel, so I get negative x. So e to the negative x is equal to 1 over e to the x. Any questions for me so far, my friends? All right, now they say, hey, let's use a calculator to solve these. So using the TI calculator, I'm just going to use this one. You find the E key. So I'm going to go second E to the 5th is going to give me 148.41. Okay, it keeps going, but 2 decimals is probably fine. If I had to do e to the negative 1/3, you don't necessarily have to worry about flipping it over, but that would come out to 0.72 roughly, rounding again to 2 decimal places. And if I had e to the square root 2, oops, clear, second e to the second square root 2, close. That would come out to 4.11. Again, I'm rounding it to 2 decimal places. So be aware, I mean, I think 2 decimal places is fine. If they tell you to go to 4 decimal places, then take it to 4. But calculator will handle these very quickly, which is kind of nice. All right, tell whether the function is an example of exponential growth or decay. All right, so growth versus decay. So if you were to think about what this is, remember growth means as I go to the right, I go away from our asymptote. Okay, so we have asymptotes on these, horizontal asymptotes. If we're not adding or subtracting anything to it right now, that means it's going to have an asymptote at 0. So this first graph, if you weren't sure if it was growth versus decay, you could start plugging values in. You could say, oh, okay, what is like e to the 3rd? And if you did second e to the 3rd, oops, clear. So where is e? Second e to the 3rd, which is 3 times 1. So if you plugged 1 in, you'd get roughly 40. If you plug 2 in, so you get e to the 6th times 2. If you plug 2 in, you're getting 806 roughly. So basically, as I'm going to the right, it's going further and further away. So this is definitely a growth pattern. But this one, because I have this negative exponent, this means I'm going to have the same thing as 1 over e to the 3x. And if I do that, the bottom is going to become larger and larger and larger. So 1 over a really large number gets close to 0. So this is going to be decay, because as I go to the right, it's going to get closer and closer and closer to whatever the asymptote would be. In this case, the horizontal asymptote would be 0 because I'm not adding or subtracting anything to it. This particular problem, so this is going to get to be a very large number. Each time that becomes a large number, we're going to divide by 5. Well, a large number divided by 5 and then a larger number divided by 5 is still one bigger than the other. So this is growth. Okay, so the fraction out front doesn't do much. But when you have that negative exponent, you have to watch out for that. And this would be rewritten like this. Being that this is going to take place, that's going to allow the bottom to become big very quickly, which that's going to give us a decay. So again, remember, decay, as you go to the right, as you go to infinity in the x direction, if it grows away from your asymptote, it's growth. Okay, and it can go upward to grow away, and it can go downward to grow away. Or if I go to negative infinity, x goes to negative infinity, if I get closer and closer and closer to an asymptote, that means it's decay. It's getting smaller and smaller and smaller. All right, so here are a few methods. So let's go ahead and graph this parent function. I'll do this one in red. Okay, so a few things I know that I'm going to have this asymptote here because I'm not adding or subtracting anything to the outside. So I have that asymptote. So what I can do is, let's go e to the 0, e to the first, e to the second. So let's just verify what e to the 0 would be. What do you think? So e to the 0 is going to produce 0, 1. So you have a value there. And then e to the first is 2.7 roughly. So you get 1, 2.7 roughly. So 1, 2.7 is here. And then e to the second, and again, I'm just plugging these values into a calculator so we can kind of think about it, gives me 2, 7.4. So 2, 7.4, 7.4, someone's up here. As I get if I get negative values, that means that I'm approaching my asymptote. So as I go to negative infinity, this is approaching the asymptote. As I go to positive infinity, as I go to the right, it grows away from it. So now let's take a look at what this one's doing. Let's do this in blue. Okay, we already know all of the things that took place on here. We have a few dots. So this -2 means my graph is going to go right 2. Okay, my asymptote still stays down here. So if I move each of these points right 2, we're going to go ahead and get this for a graph. And that's what that's going to take into account. And then the third one, what's this going to do? So that 3 means my asymptote's up here. But a negative out in front, is going to flip over the x-axis. Hope that squeezes on there. Okay, so think about what my graph is doing. I'm going to look at my red graph. I'm going to go up 3. 1, 2, 3. Now I'm going to flip it over, and I said flip over the x-axis, but it really flips it over the asymptote. So this 4 is 1 above our asymptote, so it's going to come down here, back down to 2. So let's do the same thing with this. This is going to go up 3. 1, 2, 3. I'm going to flip that over. So I'm like a little bit more than 2 above, so I'm going to go down. I'm going to go down 1, 2, down like right here. And the other point, I'm going to get off my graph pretty quickly, but this is what my graph is going to look like. So again, that green one is also a growth graph because as I go to the right, as I go to infinity in the x direction, I grow away from my asymptote. Okay, is there any questions about any of those? And again, it's kind of knowing the parent function. I would use the parent function and then do the flip over and the move arounds and the jump up and downs. So I guess we should say this doesn't flip over the x-axis, it flips over the horizontal asymptote, which we'll call HA. Okay. All right, so that's it. I'm done. Wow. Okay, so I'm going to give you some time, and I need to put this on to my website. So I would like us to do worksheet 9C. And I'm pretty sure we can do them all. So I'll give you that. Why don't you take the opportunity to start working on it. If you have questions, please ask. But what I'm going to do is I'm going to stop recording now. Or was there any questions about any of the things that we had done? Okay, so let's see.